In this example, you see that the expected frequencies are already computed for us. You will use this to go through the general idea of a chi-squared goodness of fit test, but typically we're going to have to think about these. So I think a fair initial question would be, how would I recognize this as a chi-squared goodness of fit test and not some other type of test? So we're asked, is there evidence that simulated die rolls from earlier, and so this is from earlier in the handout for this section, represent an unfair die? So an unfair die might be weighted to land on one particular number more than another, right? Like maybe 3 comes up more often than the others. So the expected frequencies are based off the null hypothesis. The null hypothesis is always that an assumed distribution fits. And so what would be the assumed distribution here? If a die is fair, then what we would say is the breakdown of the number of times a number comes up should be the same. In other words, 1 dot should come up just as often as 2 dots, just as often as 3 dots, etc. So in other words, if we had, say, 60 rolls of a die, which is what this data is from, we would expect to see each number come up 10 times if it's exactly uniformly distributed. And so really what we're saying here is the die is fair. And so that's where expected comes from. It's assuming H naught is true. Die is fair means that the distribution is uniform across the dots, number of dots that can come up. And so HA would then be that the die is unfair. In other words, that we see something else that comes up. And you may say, well, okay, this is observed. This is what we actually saw happen, are these values right here. So we actually saw this, and we expected, if the die is fair, to see 10 for each thing. Now, if you really think about it, if I roll a die 6 times, it's not going to necessarily land on 1, and then 2, and then 3, and then 4, etc. There's going to be some variation here. The question is, and this is what the chi-squared test statistic will answer, are these far enough apart for me to question if this die is fair? In other words, we expected to see 10 2s come up, but we had 16. We had that happen 16 times. Is that enough for me to question if this die is fair? We expected to have 10 5s come up, but we only had 3. Is that different enough? So you think about it and you ask yourself, and you start thinking about this. It's hard to do in your mind and kind of say, well, I think that's unfair. I think it's fair. That's what the chi-squared test statistic does. So the chi-squared test statistic for this, and this is for both a goodness of fit test and a test of independence, is the sum of the observed, so it's the sum of this whole thing, minus the expected squared divided by the expected. So for each of these, we say, okay, what was observed? And we're trying to really calculate the difference. By squaring it, we take away any effect of negative numbers. And this makes it so this chi-squared test statistic gets bigger and bigger the further apart these are. And so this will always end up being a right-tailed test because we're testing is the chi-squared test statistic big enough to make me think something's going on here. So if we were to calculate this for each of these, we would say, okay, for the first, for 1 dot, that'd be 10 minus 10 squared divided by 10. I'm just going to write it out before I go doing any calculations at all. So observed minus expected, 16. So for 2 dots, minus 10 squared over 10 plus 13 minus 10. This is for 3 dots squared over 10, etc. Right? So for 4 dots, we saw exactly what we expected. For 5 dots, not quite. So the 5 dots, it's so different. It's going to contribute more. And notice I'm doing it in the wrong order. It doesn't matter because I'm squaring it. We're doing actually more here. We're going to have to see a big contribution from this because of the difference between these two. And so once again, observed minus expected, if I stick to that, squared over 10. So again here, the 3 or the 10 first, it doesn't actually matter because you're squaring the difference. Now, before I put this into my calculator, I'm going to notice, of course, this is 0, right? That's gone. This is 0. That's gone. And so I can now kind of go piece by piece and just write down what it is. There's no need to try typing this in your calculator all at once. You're going to introduce a chance of a minor calculation error. So this right here would be 6 squared, so 36 over 10, plus, difference here is 3 squared, so 9 over 10, plus 7 squared over 10, so 49 over 10. And then finally, 2 squared, so it's actually negative 2, right? Squared over 10, so 4 over 10. And when you add all of these up, you get 98 over 10, or 9.8. So the question is, this test statistic 9.8, is it big enough to make me question the null hypothesis? Because it's saying, okay, if the null hypothesis is true, this is the difference between what we saw and what we would expect. Does that make me question the null hypothesis? And so, like I said, the bigger, the more we question it, because that implies a bigger difference. So this is always a right-tailed test. And so to get back to my earlier point, whenever you're testing, does something fit? Is it a fair die? Does it follow a binomial distribution? That's a goodness of fit test. Independence tests are really obvious because you're usually asking for a relationship or not. All right, so as with every test, we have our H non HA, we have our test statistic, and now we need a rejection region. And so this will always be a right-tailed test. And so we're going to put alpha on the right-hand tail. So this is a 10%. And now I need to know which chi-squared distribution am I looking at? Well, degrees of freedom will be the number of groups. So we got 6 minus 1, so we get 5. And so when I look this up on the table, degrees of freedom 5, I'm looking for a 10% area to the right. I get 9.2363. As you can see, the 9.8 is just a little bit bigger than that, right? So it ends up maybe about right here if I was trying to visualize where that 9.8 is. And so that means automatically, since I have 9.8 bigger than my 9.2363, we're in the rejection region, so I reject H naught. And I say, yes, there is evidence that this is an unfair die. And so notice how close this was. This is a reflection actually of alpha being 10%. This means probably the p-value is just barely under 10%. And if I remember correctly, I actually looked it up, it's about 8%. So we would have had the same conclusion, but those always correspond. So the p-value is actually the area to the right of the test statistic, since this is a right-tailed test. So you can imagine the p-value is only a little bit smaller than alpha, but you still come to the same decision. So as you can see, the procedure stayed the same. Hypothesis testing always has a null hypothesis, a test statistic, and then you can either use a rejection region or a p-value to make your final decision in interpretation.